Hi. Let us briefly discuss several interesting papers which appeared in the arXiv in the second half of March. So, in the first place, I'd like to note that there are several very interesting reviews published in March. I just briefly mentioned them, showing my Russian page of the project of my reviews of interesting papers in the arXiv. So there was a large review on string cosmology. What is surprising for me that it is quite understandable. Not the whole review, of course, because it's very large and complicated, but still one can find some understandable parts, not being a specialist in string theory. So that's quite interesting. Then there was a paper about which I also will not talk in details. That's a very technical paper about new Japanese satellite. This is an X-ray satellite, an X-ray telescope, and it is supposed to be launched this year. So this is quite interesting. The project is called X-Reason. Then there was an interesting review about binary evolution. Really, it's very interesting because it covers lots of different topics. It covers mainly very briefly these topics, but the review is very wide. So I really recommend to have a look at it. Then there was a review about searches for violation of Lorentz invariance. That's also quite interesting. Then there was really a nice review about the first stars. Mainly the authors focus on their formation and properties, as it is marked here, as it is mentioned in the title. The authors, they do not pay much attention to the remnants of the first stars and to explosions of the first stars, so it's not the main topic, but all the rest I think is covered very well. There is a brief but very interesting review about black holes. Mainly the authors tell us about two well-known examples of supermassive black holes for which radio images of the flow around were obtained. But what is important, many interesting aspects related to accretion onto these black holes are discussed. On one hand, in details, but on the other hand, this is really a popular review. It's written for Nature, so it's more or less for general public, I would say. And then it is quite understandable. And finally, there are two new catalogs of X-ray binaries. That's the first paper. That's a catalog of high-mass X-ray binary systems. And then there is another paper. Here is the number, in which the authors present the catalog of low-mass X-ray binaries. Okay, but now I want to talk about four papers in details, and of course, they are original papers. So the first one is about microlensing observations of free-floating planets. So typically when we speak about planets out of the solar system, we're thinking about exoplanets. These planets orbit around a star, or maybe a binary star, or a neutron star, or around a white dwarf, something like that. But there are many isolated planets, free-floating planets, and they can be discovered by different techniques. In some cases, it's possible to obtain images of these objects, but only for gas giants. That's the first thing. And then only if they are young. Because in this case, they emit light by themselves. Young planets, young gas planets, are still contracting, and so they have additional source of energy. They are hot, and so they can be detected in infrared. But if we want to study the general population of free-floating planets, we have to use a different technique. And the best results are obtained with the gravitational microlensing. And so in this paper, the authors focus on this. The number of microlensing events on isolated planets is not huge, is not impressive. There are about a dozen of well-known events discovered in the project in which the authors are involved. And so I have to underline that their conclusions are based on a rather limited sample, but in few years, with the next space telescope, with WFIRST, with the Roman telescope, the number of such events will be much larger, and so results are going to be more precise, but at the moment we have what we have, and what we have. The authors analyzed this sample, and let us look on the plot. On the horizontal axis, we have masses of objects in the units of the Earth mass. And we have stars on the right, then brown dwarfs, and this dotted blue line shows the contribution of these sources. And then we have free-floating planets, this green dashed line. And we see that planets start to dominate among isolated objects. So we're speaking about free-floating objects. The green line shows microlensing data for the mass distribution of bounded planets. So planets which orbit around some star, or maybe around a white dwarf or a brown dwarf or another object. But typically in this sample, they orbit around normal stars. And if we believe to the conclusions of the authors, then the number of free-floating planets is really large. The number of free-floating planets is about 20 per star. So these objects, according to the authors, are more abundant than bound planets. And in this case, especially taking into account that they, I would say, predict in some sense the existence of lots of isolated light planets with masses around the Earth mass or even lower, then these objects were ejected from systems at the stage of formation and early evolution, so they were not formed isolated from the very beginning. So they didn't form like stars and the majority of brown dwarfs, but were ejected from different systems. This is quite an interesting result. And well, let's wait for confirmation from finally from the WFIRST. Okay. Another paper I want to mention, this is a record using the James Webb Telescope. The authors discovered an active galactic nuclei at the redshift larger than 8. So this is roughly the epoch corresponding to 500 million years from the Big Bang, slightly more than 500 million years. It is possible to estimate the mass of the black hole, and in this plot it is shown with this yellow or golden star, if you like. There are many objects at smaller redshifts. This is still impressive, 6, 7, up to nearly up to 8. But this object is in the early epoch. And an interesting question arises, what's the origin of this black hole? There are several channels to produce seeds for supermassive black holes. So two main channels are stellar remnants, remnants of the population 3 stars. Population 3 stars are the first stars in the universe with, say, formally zero amount of heavy elements. But in some cases, it seems that that's not enough, because these seeds initially have masses about 100, 200, maybe solar masses. But in some cases, we need more massive seeds, because quite massive black holes are detected at relatively large redshifts. The growth of black holes during the evolution of the universe is shown here by the blue dashed line. This line corresponds to a typical seed originating from POP3 stars, and by this red dotted line and red dashed line, they correspond to more massive seeds. So masses are on the left. As I said, for POP3 stars, seeds have masses about 100 solar mass, so log of the mass is 2. But in some cases, we need more massive seeds, and they have masses from, say, 10,000 solar masses up to maybe 1 million in some case. And they, of course, can grow more rapidly and produce massive black holes at redshifts 7, 6, with masses above 100 million solar masses, even close to 1 billion solar masses. So if we have a look at this object, then the first impression is that this object was formed from a massive seed. But the authors propose a different scenario with episode of super Eddington growth, and they suggest that the seed could have initially the mass about 100 solar masses. But again, it's interesting to study this object in more details, to model its evolution in more details. Still, such records are welcomed because they really bring us some new questions, some new ideas, and this moves science forward. Well, the third paper I wanted to talk about, again, it's a kind of a record. The authors discovered a planet. This is a massive planet, a giant. It's orbiting about a subgiant star. Subgiant means not like it's a fake giant star or something like that. This means that the star already left the main sequence and is moving during its evolution towards the branch of giants. So what is interesting about this planet? The authors obtained independent measurements of the mass and the radius of the planet. So it's possible to measure the average density of the planet, directly measure. And in this plot, of course, the planet is shown with a red circle, and there are other planets and brown dwarfs on the right. So density is on the vertical axis and planetary mass on the horizontal axis. And you see that this object formally belongs to planets. It is in this shaded region, which is formally a region of overlapping between brown dwarfs and planets. There is no one universal value which separates brown dwarfs from planets, but this object is a planet, and it has a very large density. Still, it's not a miracle, of course. As you see, there is a general trend from giant planets towards brown dwarfs. The density is growing, and this object is where it might be. But it's interesting, of course, to find such planets. That's important if we want to study them. Okay, and finally, the fourth paper, also about a planet. And this is a Nature paper. And this is about the famous system Trappist-1. So there are 7 known planets in the system, and the authors detected with the James Webb Telescope, as you can imagine, directly detected thermal emission from this planet. This planet is Trappist-1b. This is the closest planet to the host star. It is out of the habitable zone. Maybe you remember that 2 planets in the Trappist-1 system are in the habitable zone. I would say at least 2 planets are in the habitable zone. This one is not. It obtains about 4 times more energy than the Earth gets from the sun. So it is inside, close to the star, out of the boundary of the habitable zone, inside, in terms that the orbit is inside the circle which shows us the habitable zone. How they were able to measure the thermal flux of the planet and what they learned. They measured what is shown in the picture. They measured the secondary eclipse. So this tiny drop in the flux which we get from the star, all planets around, corresponds to the moment when the planet, Trappist-1b, is behind the star. So we don't see the planet. And so this drop allows us to measure what was the contribution of the planet to the total flux of the system. The planet might be tidally locked, and it's possible to show that the light mostly comes from the day side of the planet. On one hand, that's not a miracle, but if you look into details, then you can say that this is really a day side. I mean, it's really hot, and it's really hot because there is no atmosphere, or the atmosphere is very thin. If a planet has a thick atmosphere, then energy is distributed more uniformly on the whole surface of the planet. But if there is no atmosphere, then the day side is much hotter than the night side of the planet, and so it can be derived from observations, and we can learn something about the properties of the atmosphere of the planet. That's very interesting because, as you remember, studies of atmospheres of planets around red dwarfs, and Trappist-1 is a red dwarf, studies of the atmospheres of planets around red dwarfs can allow us to look for life, actually. And planets, of course, in habitable zones around red dwarfs is a very important target for, well, in a sense future, but really very near future studies. And it's very interesting to understand, in general, dynamics of atmospheres of planets around red dwarfs. And these studies of Trappist-1b can be an important step, and that's why the paper is submitted to Nature. Okay, so here we are. These are some interesting papers which appeared in the arXiv in March. Well, there'll be also 3 more days with releases of papers in the arXiv dated by March 2023. So maybe in these 3 days some more interesting results appear, but we'll see. Okay, good luck. Have a nice time. Read papers. Again, I underline that there were many interesting reviews published in March, so you can spend lots of time looking at it.